Good morning. All right, we have a lot to cover today. Gauss's law. We're going to do lots of Gauss's law problems. But for the exam coming up, this exam is really nice because it's just such a nice small amount of material, and it should be completely obvious what you have to do to prepare for it. I often tell my classes, if you're surprised by anything on this exam, there is something severely wrong with the way you're preparing. Let's take a look at Chapter 5. Chapter 5 is all about integrating over a charge distribution to find an electric field. Well, I told you you were only going to get one-dimensional charge distributions. How many different ways can I draw a line? I'm not that creative. I can draw a straight line segment. I can draw a curved line segment. That's about it, right? So make sure you can integrate over straight line segments, curved line segments, and find electric fields. That's what Chapter 5 is all about. Chapter 6 is all about Gauss's law. And I told you there's only three different symmetries where Gauss's law is helpful: spherical symmetry, cylindrical symmetry, and infinite sheets of charge. So make sure you can do those three, right? Work on those three examples. And that's what this exam is all about. Okay, let's get busy because we've got some things to cover. So we were talking about shielding last time, and let's just talk about that a little bit more. So if we have a conductive shell, so this is our conductor. Oops. And there's a hole or a cavity in the center of it, right? Just a shell, a thin conductive shell. And we put an electric field outside of this shell. What happens to it? The charges in that conductor feel forces because of that electric field. Positive charges want to go in the direction of the electric field. Negative charges want to go opposite the direction of the electric field. So the electrons want to go opposite the direction of the electric field. They start moving in that direction, and they keep moving in that direction until the force causing an electron to move in one direction equals the force pushing back on it from the electrons that have already moved. And then the electrons stop moving, and we have a situation we call equilibrium, right? The charges are no longer moving, they are static equilibrium. So our charges move. We get a negative charge over here, and we get some positives left behind over here. And what happens inside? In the conductive material, E is 0, right? And inside the cavity, in the hole, inside that shell, E is going to be 0. Okay? Now, let's think about this situation. We'll take our conductive shell, and we'll put a charge inside of it. What's going to happen? Here, I'll just do it. What's going to happen? Draw the electric field lines everywhere. So this positive charge is going to fill the space around it with an electric field, right? The lines are going to come out from this positive charge. It's fixed, pardon me. It's fixed in place. It's going to fill the space around it with an electric field. But inside that conductor, what's going to happen? As soon as we get an electric field inside that conductor, the electrons are going to feel a force toward the inner surface. So electrons are going to keep moving toward the inner surface until they have exactly canceled out the electric field, and the electric field is zero in the conductive material. So we're going to get some electrons here on the inner surface. And the electric field is going to be zero in that conductive material. Well, that conductive shell was electrically neutral. So if a bunch of negative charges move to the inner surface, what does that leave behind on the outermost surface? A bunch of positive charges. And what do positive charges do? They emit electric field lines. So if you're standing outside, looking in, what does it look like to you? It looks like plus Q at the center there. You can't even tell that there's a conductive shell around it. It looks exactly the same as if there was no conductive shell there. So the conductive shell shields electric fields from getting inside the shell. Electric fields that are outside the shell are shielded. They can't get into the shell. But electric fields from inside can get out.
Question.
Go ahead, Swift.
Does it matter what shape is this conductor?
It does not matter.
Thank you.
Okay, now I know what you're thinking. You're thinking, wait a minute, haven't I seen something like this before? When when you heat something up in a microwave oven. So what did we do last time? Last time I put that cage right over the electroscope, that mesh, that wire mesh cage over the electroscope. we could still see through it, but it was shielded from the electric field. When you look through the door on your microwave oven, what do you see? You see a metal mesh cage there. It turns your microwave oven into a Faraday cage to protect you from the electric fields that are inside the oven. How does that work? Well, let's take one more look at this situation. We'll add a different case here. Let's take our conductive shell. And this time, it's supposed to be, it doesn't matter. Whatever. Plus Q in here, right? This time, we're going to ground the shell. So we're going to attach this to ground. Ground is a reservoir of charge. So when we put that positive charge inside the shell, this is one way to think of it. When you put the positive charge inside the shell, it attracts electrons. Where are they going to come from? They're going to come from this reservoir of charge, ground, and work their way up. And so we're going to end up with our field lines coming out here. We're going to end up with our negative charges all around the innermost surface. But the outermost surface is going to be neutral because these electrons didn't come from the outermost surface, they came from ground. So now our conductor is not electrically neutral anymore. It has a net negative charge on it. Those extra negative charges came from ground, and the electric field is zero inside the conductor, and the electric field is zero outside of the shell. So another way to think of it, if you prefer, is that the negative charges move in to the innermost surface. They leave positive charges behind, right? Those positive charges want to get as far away from each other as they can, right? They're repelling each other. The only force they feel is from the other positive charges. Once the electrons move into the innermost surface, they are shielding those outer positive charges from anything inside the shell, right? The electric field is zero inside the shell. So those positive charges want to get as far away from each other as they can. So they end up on the outermost surface of that conductive shell. But if we connect it to ground, they can now go farther away from each other by all going to ground. Ground is sort of this infinitely large reservoir. So the positive charges want to get away from each other. As soon as we give them a chance to get farther away from each other, as soon as we give them a chance to go to ground, they bolt, right? They go to ground. So that's why your microwave oven protects you from what's on the inside. It's grounded. It's grounded. Okay. Questions? Good. Where are we? Okay, question. The positive charges go to ground. No, but that we can think of it that way. It's a perfectly fine way to think about it. As far as we're concerned in electrostatics, if you think about the negative charges moving one way or the positive charges moving the other way, they both work, okay? So that's why I talk about positives moving to ground. Really, negatives are coming, the picture is correct, right? Negatives are coming from ground, electrons are coming from ground to our conductor and canceling out those positive charges. But if you prefer to think about it the other way, that's fine. Yes, this is going to be on the exam. If E is 0 inside the conductive shell, if E is 0 inside the conductive shell, and there's a charge inside the conductive shell, does the charge inside the conductive shell experience a force? Well, first of all, E would not be 0 inside the conductive shell if there was a charge inside the conductive shell. So the shell shields the inside from any external electric fields. The only way to get an electric field inside of the cavity of that conductive shell is to put a charge in there. So if there's no charge inside the shell, then E is 0. If there's a charge inside the shell, then there's an electric field due to the charge inside the shell. That charge would not experience any force because a charge cannot exert a force on itself, right? If you can't exert a force on yourself and you're the only thing in there causing an electric field, then you won't experience a force. There'd have to be two charges in there, then they would experience a force. Let's see, once the electron move into the conductor. I think I've answered that question. Question about which charges are moving. Only the electrons move, right? We know that. But if you prefer to think about positive charges moving, if it makes it a little easier for you to picture what's going on, that's perfectly acceptable in electrostatics. In fact, that's what we do in all of our circuits. Someone, I believe it was Benjamin Franklin, picked, right? But they didn't know which charge, they knew charges moved. They knew it was either the positive charges that moved or the negative charges that moved. And the story is that Benjamin Franklin guessed positive charges move. And so they came up with all of our formulas are based on the direction of the current in a circuit being the direction positive charges move through a circuit. Then later on, we discovered it's not the positive charges that move, it's the negatives. But they didn't change any of our formulas. They all are based on positive charges moving in one direction when we know it's really negative charges moving in the other direction. So for almost everything we do, you can view it either way. Positive charges moving one way or negatives moving the other way. What happens if you stop grounding the conductor? You just have to ground it momentarily because nothing's changing here, right? Everything's static here. There's just a charge sitting inside that shell. So as soon as you ground it, just for a split second, a second, I don't know, not very long, just enough time for the electrons to come up and cancel out the positive charges. Then once that's taken place, you can remove the ground and no electric field will come out. Now in a microwave oven, the electric field is constantly changing. So you would have to remain grounded the whole time in that situation. But here, there's just a charge sitting there, it's static, nothing's changing. So you just have to ground it for a second or two. Ground is a reservoir of positives and negatives. It can accept electrons or supply electrons. So on the outside, there's no net charge and no that's correct. Why the electric field in the conductor is 0? The electric field in the conductor is 0 here, even though there's a net negative charge on the innermost surface, because there's a net positive charge inside the cavity, in the hole there, right? So if we were to draw, let's just do one here real quick. If we draw a Gaussian, I'm going to make my shell a little thicker. Okay, so here's our conductor. Here's our plus Q. This is a hole in here, right? That's the conductor. So the negatives get attracted to this surface, right? If we draw a Gaussian, spherical shell, right? Remember, a Gaussian surface is this imaginary surface we impose on our charge distribution. And we say, we know the integral over that Gaussian surface of E dot dA has to be the charge inside over epsilon naught, right? So we know inside of a conductor in electrostatic equilibrium, the electric field has to be 0. So we have 0 on the left side of our equation. So if we have 0 on the left side of our equation, epsilon naught is just a constant, right? So Q inside our shell has to be 0 according to Gauss's law. Well, that means whatever charge we have inside the shell, we have to have an equal but opposite sign amount on the innermost surface. So if we have plus Q inside the shell, then we have to have minus Q on the innermost surface. The electric field inside of a conductor, a solid conductor, would also be 0 if it's in electrostatic equilibrium, okay? That means that, so we can have electric fields inside of conductors, right? Like the wires in our walls that make current flow and our electronic devices work. You flip the switch and an electric field is inside the conductors and the charges start to move, because charges in a conductor are free to move. And if they're in the presence of an electric field and they're free to move, they're going to move, right? The positives are going to, well, positives don't move, but the negatives are going to move opposite the direction of the electric field that we set up inside those wires, right? So it's only when the charges stop moving. If we have a conductive material and the charges are not moving, that means they're in electrostatic equilibrium. The charges are static, right? They're not moving. Then we know for certain the electric field inside of that chunk of conductor has to be 0, because if it wasn't, the charges would move, right? The definition of a conductor is charges are free to move in a conductor. And if it's free to move and there's an electric field pushing on it, it's going to move, right? So, so any solid chunk of conductive material, when we set up an electric field inside of it, the charges start to move. And when they stop moving, we know the electric field has to be 0 in that conductive material. And if we cut a hole, a cavity out of the inside of that and make that solid conductor into a shell, the shell acts the same way. The shell acts the same way. Okay, I'll check. I'll tell you what, I'll look at that during the break. Okay, good, excellent, good questions. So now let's take a look at a cylindrical charge distribution. Last time we did spherical charge distribution using Gauss's law. That's pretty straightforward. Let's take a look at cylindrical, although we can do more spherical if you need to, that's fine. Okay, so let's do one that we know the answer to, because we can do an infinite line charge, right? We can do an infinite line charge and find the electric field away from an infinite line charge. So let's do an infinite line charge. So we have our infinite line of charge. Here's a side view. And we have, here's the end view. Right? If you're just looking at that line of charge from the end, all it looks like is a point charge. If we rotate it 90 degrees, it looks like a line. And the electric field is going to come out in, if we're looking the side view, it's kind of going to look like this, right? And if we're looking at the end view, it's going to look like this. So we have cylindrical symmetry, right? Even though it's a line charge, whether this is a line charge or whether it's a cylinder with a radius, an infinite cylinder, it looks kind of the same, right? It's the electric field would look the same. So this has cylindrical symmetry. So we would pick a Gaussian surface, right? So this is not terrible to find the electric field from this, but we can do it using our chapter 5 techniques. We can integrate over the whole line distribution, line charge distribution from negative infinity to positive infinity, and we can find the electric field. It's not too bad, but I think you'll see it's much easier using Gauss's law. And let's think about if it wasn't a line charge. Let's think about if this was a cylinder like this, with charges spread out all over the surface of that cylinder. And we wanted to know what's the electric field over here. Well, there's something here producing electric field that points in that direction, right? There's some little charge back here that has it pointing this way. You'd be integrating over the surface of that cylinder if the charge was only on the surface of the cylinder. If the charge was spread throughout the volume of the cylinder, you'd be integrating over the volume of the cylinder. You see this gets ugly really fast. using the chapter 5 approach to solve this problem. I've simplified it by making it a line charge, but the technique for solving it using Gauss's law is the same if it's a line charge or a cylinder with a radius. It doesn't matter. It still has cylindrical symmetry. So let's take we want to put our cylinder in here, our Gaussian surface. We want to know what's the electric field at some point a distance r away from this line charge, right? So what's the electric field here, right? So what do? We put the surface of our Gaussian surface of our Gaussian shape, right? We put the surface at that location, right? Because we want that dimension to show up somewhere in our calculation. And we want to match the symmetry of the problem. Remember, we're solving this kind of an integral. We're solving the integral of E dot dA. So we want our surface to always have an area vector that's parallel or perpendicular to E, because those are the two easiest cases to solve, right? And we want E to be constant everywhere on our surface. So we would pick a cylinder oriented with the same orientation as our charge distribution, right? So a side view, our cylinder would look something like this. Oops, I missed. That's okay, I can fix that. And looking at the end view, our Gaussian surface would look like this, right? So we pick a cylinder because that matches the symmetry of the problem. Now we want to do this integral. Well, what does that little circle mean? That little circle means we're integrating over every side of our enclosed surface. So if we pick a cylinder, right, it has a top, it has a bottom, and it has this curved surface around the edge, right? So we need to integrate over all three of those. So that little circle, if I want to get rid of that little circle in the integral sign, I have to break this up into three integrals over each of those, one over each of those surfaces. So I've got, this is the same thing as saying the integral over the top of my cylinder of E dot dA plus the integral over the curved surface of E dot dA plus the integral over the bottom E dot dA, and that has to equal Q inside over epsilon naught. Okay, so that little circle on the integral sign means I'm integrating over the whole, all the surface that encloses some region of space that has that Q inside of it, right? This is a closed surface. It has an inside and an outside. So for a cylinder, that means there are three surfaces. There's the curved surface, the top, and the bottom. You thought that was just there for my drinking pleasure. Okay, let's do it now. So what's the flux through the top surface? 0, right? The electric field lines are skimming the surface. They don't penetrate the surface, right? They are skimming the surface. Another way to say it is E and dA are perpendicular. So we get a cosine 90 degrees gives us 0, right? And what does this one give us? Over the curved surface, E is constant, right? Because E only depends on how far away. You have to know, in order to use Gauss's law, you have to know a little something already about the electric field. And in this case, we can sort of see that it's going to depend on the radius. So if we're at the same radius all the way around, which we are on this Gaussian surface here, right? We're at the same radius all the way around. So E is going to be constant. And and the dot product is just going to give us a cosine of 0 degrees, which is 1. So we end up with E times the area of the curved surface. So I have E times A is equal to Q in over epsilon naught. And it's just the curved surface, right? So what's the area of that curved surface of a cylinder? It's this distance, 2 pi r, times the height, right? Because if had a if this was our if this is our cylinder, right? We could cut it down the side and open it up. This was 2 pi r. This is the length or the height of the cylinder. I usually use h, but so we have so E times the area of our Gaussian surface, 2 pi r h, is Q inside over epsilon naught. And we're trying to find E, so let's move everything over. I like to group my constants together. And then I've got a Q in over H and a 1 over R. So my electric field drops off as 1 over R as I move away from my line charge. But something here bothers me. It has an H in it. So the R is okay, right? The R tells us how the electric field depends on our distance away from the line charge, right? Which is good. We need that in our answer. But now I've got it depending on the height I chose. I arbitrarily chose some imaginary Gaussian surface, and I've got it depending on the height that I chose. That doesn't seem to be right, because I could choose a different height than you. We all have the same R, right? If we want to know what the electric field is 2.17 meters away from the wire, we would all put 2.17 meters in for R, right? We all have the same R, but we shouldn't have different heights. That's arbitrary. But if you think about this for a minute, Q inside my cylinder also depends on the length of my cylinder, the height of the cylinder. So let's look back here and say that Q inside is going to be all the charge on this all the charge I've sort of highlighted in green there. That's the charge inside of my Gaussian cylinder. So if I know lambda, the charge per unit length, then Q in is just lambda times h, right? So this is 1 over 2 pi epsilon naught, lambda h over h, 1 over r. And we could make it a vector quantity. It's radially outward if it's positively charged. Oh yeah, that's a perpendicular sign. No, the vectors are perpendicular. The vectors are perpendicular. E is parallel to the surface, but the area, remember how we define a surface, we use a vector that's perpendicular to the surface. So our area vector points this way for that surface, and E points this way. And so you get a cosine 90 degrees, which gives you 0. Okay. All right. So with cylindrical symmetry, like we have here, we use this. We use this. Q is lambda h, regardless of whether it's a line charge or a cylinder. Sometimes it's a cylinder, right? And the charge is actually spread out over the surface of the cylinder or throughout the volume of the cylinder. So we could have a line charge, right? And we would use lambda, charge per length of this line charge. Or we could have a cylinder with charge spread out over the surface or even through the whole volume. Doesn't matter. I've kind of drawn it over the volume surface, and we would still use lambda, charge per length, even though the charge is actually spread out over the surface area of that cylinder, or even if it was spread through the volume of the cylinder, we don't care because it's a long, thin thing. And the way we're going to solve this problem is by looking at the charge per unit length and use the fact that we have cylindrical symmetry. Because the charge isn't changing as we're moving along the length, it's uniformly distributed that way. It doesn't have to be uniformly distributed through the radius of the cylinder. It has to be uniformly distributed about the length of the cylinder. Then we don't care whether it's what it really looks like. Because if you're outside of a cylindrical charge distribution, it looks like a line charge at the center. Just like if you're outside of a spherical charge distribution, it looks like a point charge at the center. Okay. Let's do this. Quick question here about flux. So what do we have here? We've got two spheres. We're seeing kind of a cross section of them, and different Gaussian surfaces we're imposing on the problem. So one of them is a conductor. So the one on the left is a conductor, and the one on the right is an insulator. And the insulator is uniformly charged throughout its volume. They both have the same charge, plus Q, you see that? One is a solid conductor, the other a solid insulator. The insulator uniformly charged throughout the volume. And we've got these five different Gaussian surfaces. A is this one here. Okay. B is this big square that cuts through half of our sphere. C is the same size as A, but it's over here just capturing a little bit of that sphere. D is this yellow line. It didn't come out well on the photocopy machine, but D is this thing here, and so it's the same size as A, and it's also at the center. And then E is just like B. It cuts the sphere in half. Cuts the sphere in half. Okay. So you're trying to figure out the electric flux. Rank the electric flux through each of these surfaces. And if any are zero, indicate that in your ranking. Include 0 in your ranking. And if any are tied, make sure that's clear. Okay, so are we going to try to integrate over surfaces to find the electric flux? No, we're going to use Gauss's law and say the electric flux is equal to Q inside over epsilon naught. So for A and B, those are pretty straightforward, right? If you put charge anywhere in a conductor, let's say we could magically reach in and inject those charges to the center of that conductor, those charges are free to move. All that excess positive charge repels itself and moves to the outermost surface, right? And because charges repel and they're free to move, they are going to uniformly distribute as far away from each other on the outermost surface of that sphere. So we know that A contains no net charge inside of it. All the excess charge is on the outermost surface of this conductive sphere. So A is going to be 0 because Q in is 0. B is going to contain exactly half of the charge because the charge is going to be uniformly spread over the whole surface, and B cuts it right in half and includes exactly half of the sphere. So B has half of the charge. The other ones become a little tricky, right? E also contains exactly half the charge. Even though we uniformly spread the charge throughout the volume of that sphere. Now, an insulator, the charge has to stay where we put it. So if we put charge all throughout the volume, it has to stay there. It can't move around in an insulator. So it stays there. So if that sphere is uniformly charged throughout its volume and we cut it in half, each half is going to have half the charge. So E is going to be exactly the same as B. D has some charge, but less than half. Did they tell us what the radius was here? Yeah, the radii of A, C, and D are half of the total radius. So if the radius is half as much, the volume is going to be a lot less than half, right? So D is going to be less than half. C is going to be less than D. C just has a little tiny bit of charge, right? But more than zero. I think that's right. Is that what you got? So B and E are the greatest, and they're the same. D was next, right? Followed by C, followed by A, which is equal to 0. A contains no charge, right? A is right here. And all the charge, this is a conductive sphere. All the charge goes to the outermost surface. So all this plus charge has to be, those are plus signs, has to be on the outermost surface, nothing inside. So A contains 0 charge. So it has to be 0. C contains a tiny bit of charge. Little tiny bit right there. So it has to be more than 0, right? Because flux is proportional to how much charge is inside of the surface. C has a little tiny bit of charge inside the surface, and D has more, but less than half. Okay. Anyway, it's a good idea to understand flux a little bit, not for the sake of flux. People, once you get out of physics 4b, you're not going to be asked about flux, but you're going to be asked about electric fields. And it's a tool, it's a technique we use that makes it much easier to find electric fields for certain symmetries, right? Spherical, cylindrical, infinite sheets. So we'll do some more after our break. We'll do infinite sheets, but the important thing is being able to use it in Gauss's law, right? That's why flux is important. We do deal with flux later on with magnetic flux. That tells us a lot too. So getting the hang of it now and kind of getting a feel for what causes it to change is important. Okay, so we'll take a break, come back at 5 after.
Hey,
I'll pause the
Professor.
recording. Okay, we're back. I want to do this now? Not yet. So let's take a look at the surfaces one more time. Let's do our conductive shell. So here's our shell. We've got a positive Q at the center. So go ahead and draw the electric field everywhere. This is a neutral conducting shell. So inside our shell, we've done this one already, but inside the shell, inside the cavity, it fills the space with an electric field. The negative charges are brought to the innermost surface, so we're going to end up with some net charge on that inner surface. They're going to leave some positives behind. Something like that. I think I have too many pluses here. Anyway, there we go. And then we're going to get electric field outside. But E is going to be 0 in there, okay? So question is, what are Q inner and Q outer? So there's going to be some charge here and some charge here. What are those? So when we draw our Gaussian surface, should use a different color than red, maybe. If we draw our Gaussian surface here, then we say the integral E dot dA is Q in over epsilon naught. And what does A have to be inside of that conductive material if it's in equilibrium? 0. So that means Q in has to be 0. And that is equal to Q Q in is equal to Q at the center, capital Q, plus Q inner, right? So I've got in and inner, sorry, they're different. Q inside my Gaussian is Q on the inner surface plus capital Q. Maybe I should use Q enclosed here. Let me change this, hold on. Q enclosed by my Gaussian surface has to be Q inner plus capital Q that's inside the cavity. And so those have to be equal and opposite, and that's 0, right? So Q on the inner surface is opposite, equal and opposite to what's in the cavity. That's always true. Always. The innermost surface equal in magnitude, opposite in sign to the net charge in the cavity. So that's the easy one to find. The next one we want to find is Q outer. Well, if we know the net charge on the shell, then we can find that next, because we know that Q inner plus Q outer has to equal the net charge on the conductive shell, right? Because on the conductor, that's where excess charge always ends up, on a surface somewhere. So excess charge won't just hang out in the meat of the material of the conductor. It'll be on the outermost surface or the innermost surface or on a surface. So Q inner plus Q outer has to equal the net charge on our shell. And in this case, it was neutral, right? So it's 0. And so Q inner plus Q outer was 0. And so we end up with Q outer is equal to plus Q. Okay, so finding those surface charge densities, either surface charge for spheres, we usually just find surface charge. For cylinders, we could do the same thing, but it would be lambdas, right? Surface charge, sorry, it would be charge density lambda. Charge density lambda. Okay, should we try? Let's do this one. So here they've got we've got a charge at the very center there, capital Q, positive charge. And then there's a conductive, so we've got a charge at the center, capital Q. We've got this conductive shell here. I'm going to highlight it in green. That's our conductive shell. And then these two dashed lines are Gaussian spheres. It's a spherically symmetric charge distribution. So in A, it says the two Gaussian surfaces at A and C have the same flux. They have the same flux. So what is the inner and outer charges? What is the charge on the inner and outer surfaces of the conducting shell? First, you would want to find the net charge on that shell, right? So if A and C both have the same flux, what's the net charge on that conducting shell?
Zero.
Correct. So if it means, right, it means that they both have the same, the flux through A, that's not what I wanted. So they both enclose the same amount of charge, right? If they both enclose the same amount of charge, the shell must be neutral, right? That's the flux through A is proportional to the charge inside of A, right? That's this one here. And it has capital Q charge enclosed. The flux through C is proportional to the charge inside of C, and it's the same as A. So the only way they could both have the same charge is if that shell is neutral. So if it's neutral, then we can find the inner and outer, right? What's the inner have to equal? Yes. The inner surface is always equal in magnitude to what's inside the hole, what's inside the cavity, but opposite in sign. So minus capital Q. And if both of these have to add to 0, if Q inner plus Q outer has to add to 0, then Q outer has to be plus Q. I guess they put a Q naught there. Okay. Let's try the next part. The next one says, suppose the electric flux through the Gaussian surface C is 3 times that of the Gaussian surface A. So they're changing up the problem a little bit on us. If the flux through C is 3 times A, then what are the charges? What's the charge? Yeah. Q inner does not change, right? That's still minus Q. And Q inner plus Q outer has to be positive 2. So we know that A has positive Q inside of it, and C has 3 times that amount inside of it, 3Q. So C also has the same Q that A had. So where is the extra 2 coming from? Has to be from the shell. I think I'll leave C and D for you to do later. Those are the same type of thing. Okay. See if you can do C and D later based on the answers to A and B. No. Question about the inner and the outer surface. A is inside a Gaussian surface A is here. This is a Gaussian surface inside, smaller than the shell, inside of the shell. The shell is out here. That would be the inner radius of the shell, and this would be the outer radius of the shell. The shell is very thin. And then outside of that is C. That's a Gaussian surface outside of the whole thing. Does that help a little bit? The shell is very thin right in here. Oh, question about, can you think of it? Yes, the innermost surface is always equal and opposite to everything inside of that cavity. And the outermost surface is equal to the net charge of everything, of the shell plus everything inside of it. The outermost surface is always the net, add up all the charge, the shell plus everything inside of it. That's what the outermost surface is always. Because when you're standing outside looking in, it's as if that shell is not even there, right? You have to see the total charge that's in that it's in that spherical distribution. So for B, one more time, the shell has to be 2 because we know A has positive Q inside of it, and we know C has 3 times as much charge inside of it, which means it has to have 3Q. One of them is already at the center. So where are the other 2Q coming from? It has to be from the shell. Why is this going crazy? It's not. Okay, so here we have, take a look at it later, but there's a charge, there's a Gaussian surface at A. Then there's a shell, a conductive shell. Let's use black here. A thin conductive shell. And then there's another Gaussian surface outside of that. So if we know the flux through A is the same as the flux through C, we should know that they both contain the exact same amount of charge, right? This is all based on flux equals Q in over epsilon naught, right? Okay, so take a look at that. We're comparing the flux through A and the flux through C. Both A and C contain this charge at the center, the plus Q at the center. So any difference has to be due to the charge on the shell. Any difference between C and A. If C has 3Q and A has 1, then where's that extra 2Q of charge coming from? It has to be from the shell. Okay, so check that out later, because we need to get to infinite sheets. Okay, so let's just take a look at a point charge. It fills the space around it with an electric field, right? Now, if we link multiple point charges together to make a little charged rod, it looks something like this, right? And the electric field looks kind of like this. Maybe there's one here, something like that. Now we're going to link more. We're going to make it longer and longer and longer. And what's the electric field look like? Something like that, right? So what's happening as this gets longer and longer and longer, the electric field lines are becoming more uniform, right? They're becoming more parallel. And only the edge effects are changing that, right? So if we had one that was infinitely long, then the electric field lines would all be parallel. Okay. And the same is true. Yeah, same is true for infinite cylinders. So this, if this is a line charge, if this is just a line of charge, this is like a cylinder, right? So the an infinite cylinder, the electric field lines come out parallel, but when we look at the end, they're diverging, right? So the electric field gets weaker as we move away from the field line. But think about what happens now if we take this point charge and we made it infinite in one dimension, right? What happens if we make it infinite in the other direction too and turn it into a sheet of charge? If we turn it into a sheet of charge, then the electric field becomes uniform in both dimensions, right? So we want to figure out what that electric field is. We've got this infinite sheet of charge perpendicular to the plane of the page. We want to figure out what that electric field is. So we want to find a Gaussian surface that matches the symmetry of the problem, that whose sides are either perpendicular or parallel to the electric field lines. And so how would we orient it? This, of course, would be caused by a sheet of positive charge, right? This is a sheet of positive charge, where the electric field comes out from the positive charge. So we would want to orient, we could choose any number of things. We could choose a box, right? Some kind of a rectangular box. That would work. If we use this as our Gaussian surface, or we could use a cylinder in this orientation. That's not a very good cylinder, is it? A cylinder in this orientation, because that also has sides that are parallel to the electric field line or perpendicular to the field line. Either way, I'm going to use a cylinder because a cylinder only has three faces I have to worry about. The other one has more. All right, so here's our charge. I'm not going to try to draw it in. It's as a infinite sheet. All right, so my electric field lines do this. I'm not going to try to draw in 3 dimensions. It's bad enough in 2 dimensions, right? So we draw a Gaussian surface in here, and I'm going to pick my Gaussian surface to be a cylinder, and you have to orient it to match the geometry of the situation, to match the symmetry of the charge distribution. So your surfaces are parallel or perpendicular. You can see if you oriented this the other way, your electric field is changing with respect to the, if we oriented it this way, the electric fields, let's look at the end view. The electric field lines are all doing this, but your area vectors are doing this. So the angle is changing, right? So that's not going to be an easy integral to do. That's a tough one. So you don't want to orient it this way on an infinite sheet. It doesn't match the geometry of the situation, right? You want to orient it with parallel or perpendicular to electric field lines only. So now we say the integral around that whole surface, the closed surface, E dot dA is Q inside over epsilon naught. And I have to break, that cylinder has 3 sides to it, right? So I have to integrate over the left side of E dot dA. And I have to integrate over the curved side. And I have to integrate over the right side. Okay. The integral over the curved surface is zero. Your electric field lines are coming out like this, and they never penetrate that curved surface, right? They just come across the top of it without going through it, right? So this is 0. And the ones on the ends, that's just E times A. That's E times A. So we end up with 2 EA is equal to Q in over epsilon. And so I've got the E is 1 over 2 epsilon naught, Q in over A. And A, what is the area here? It's the area of the end of my, the end cap of my cylinder, right? The, what do you want me to call that? It's this area right here. So again, this E depends on the area of the end cap, and it depends on how much charge I have inside, but the charge I have inside is a function of the area I chose, right? So the area that gets intersected here on that sheet, that's A. I can multiply that by the charge density, right? We would have to be given, for this sheet, we would be given a charge density sigma, charge per unit area on a sheet of charge per unit area. So the amount of charge inside is sigma A. So my electric field is 1 over 2 epsilon naught, sigma A over A, sigma over 2 epsilon naught. Yes, the curve is 0 because E is perpendicular to dA. Okay, anything surprise you about this? Where's the dependence with R? How far away we are from our sheet of charge? This is a constant. Sigma doesn't change, right? 2 is a constant, epsilon's a constant. Go ahead. Did you want to say something, Swift?
No, I was just answering your question.
Okay. So the reason this is constant, well, let's not go through all the math, but picture this. Here's our infinite sheet of charge. If we're standing here, very close to that sheet of charge, because the electric field is a vector quantity, the stuff out at the ends almost exactly cancels out, right? The charge out here is producing an electric field in this direction. And the charge way down here is producing an electric field in that direction. They almost completely cancel when we're standing close to the sheet. So the charges far away contribute almost nothing because it's a vector quantity. But the charge in here contributes a lot because we're very close to that, right? Now, now let's move away. Let's move farther away. And this stuff in here doesn't contribute as much. We're farther away from it. But the stuff out at the ends is starting to contribute more because it's not canceling as much. So this one and this one, only the vertical cancels, right? It contributes something now, and it makes up for what we lost by moving away from the stuff at the center, right? We're farther away from the stuff at the center, so that's a smaller contribution, but the stuff out at the ends is contributing a little bit more now. And as you move farther out, that keeps happening. The stuff out at the ends has a bigger and bigger effect on the electric field, and the stuff at the center has a smaller effect. And it turns out that those exactly cancel, and the electric field is the same everywhere. It does not depend on distance away from the sheet of charge. These lines, with the way I drew them up here, where are they? Oh, right here. These lines are parallel to each other. What does that mean? It means the electric field doesn't change, right? Because the electric field is proportional to the density of the field lines that we draw. So if those lines are parallel, then the electric field is uniform. It's constant. It's not changing at all as we move away. Okay. So what I would like to do is limit ourselves only to insulating sheets of charge, okay? Insulating sheets of charge. This is for an insulating. Did I write insulating somewhere? There, I've written it now. Insulating sheet of charge. And after the exam, next week, we'll look at, it's a little different for conductive sheets of charge, okay? So we'll deal with conductive sheets next week. For the exam, only insulating sheets of charge. And how do we get the, if you can just know from equations on the formula sheet, how to find, don't just write down E equals sigma over 2 epsilon naught. Start with this equation, right? Gauss's law, and in a couple of lines, you should be able to show that E is equal to 2 epsilon naught. But start with what's on the formula sheet and figure out the equation for E for an infinite sheet, for a cylindrical charge distribution, for spherical charge distribution. All right. Exam covers chapters 5 and 6, right? If you look on the calendar, it tells you if we're omitting anything. But the only thing I can think of that we're omitting is conductive, infinite conductive sheets of charge, because it's a little trickier. It's really the same thing, but we define sigma differently. So it looks different, but it's really the same thing. The exam covers the same topics as the sample exam. I believe so, yeah. Okay, let's do, what should we do? A cylinder? Let's do a cylinder. Find E everywhere. Where do you want the charge? Uniform throughout the volume? Why not? So remember, for a cylinder, we treat it like any long, thin object. We just treat it like a line charge per unit length, okay? Even though that charge is distributed through the volume of the cylinder. When we solve our problems, when this is given in the textbook, you will always see lambda, okay, for a cylinder. So let's do outside first. This is an infinitely long cylinder. So we draw a Gaussian surface around the whole thing. Our electric field is doing something like this, right? And we say the integral around that red Gaussian surface. That means I can break this up, the integral over the top, integral over the side, integral over the bottom. Has to be Q enclosed over epsilon naught. The tops and the bottoms, 0, right? There's no flux through those surfaces. So we're only left with the curved surface, the side of this cylinder. And that's going to be E times the area of the curved side, right? And the area is 2 pi r h, where h is this height of my And what is Q inside? It's lambda h, right? And so the h's cancel. And I have my electric field is 1 over 2 pi epsilon naught, lambda over r. And if we put a vector, if it's positive, it's in the r hat direction. If it's negative, it's points inward. So this is a little confusing. I know, I don't know why we do it, but it's a sheet of charge. The surface is spread over the area, and that's how we solve the problem. We use the area of the sheet. We don't change the sheet and say, well, it's really like a line charge, right? So we use sigma. This charge is spread over the area. With a cylinder, even if the charge is just spread over the area, because it's long and thin, the way we solve the problem, it's as if it's a line charge. It's no different than a line charge. So as long as the charge doesn't vary, it's uniformly distributed along the length of the cylinder. We don't really care how it's distributed the other way. As long as it's uniformly distributed along the length, all we care about is lambda, the charge per unit length. And that's how we solve these things. Okay. Now, I know we're out of time, but I'll go ahead and finish this. So that's our answer if we're outside, right? If we're inside, then we've got this charge here, right? We're going to come up with a Gaussian surface that's inside this thing. So what we need to be able to figure out is the Q inside, right? So we end up with the same thing. We end up with now you have to find Q in. And so now the radius is important here, right? So we're at location little r, and this is capital R. And so you'd have to do a ratio of those areas to find the how much charge is inside of our region there, right? So the charge inside is going to be, where am I putting it? Over here. Is going to be lambda, the charge per unit length, times pi r squared over pi capital R squared, right? Maybe I'll call this lambda in. The lambda inside of our charge distribution is this, and so Q in is going to be that times H. And so you put that over here, and you get, what do you get? E 1 over 2 pi epsilon naught lambda R, something like that. Is that right? So it increases linearly. The electric field increases linearly as you move away from the origin. It's 0 at the origin, which makes sense. You will not see any non-uniform charge densities over volumes, because then you'd have to integrate. I told you I wouldn't give you any double or triple integrals. So if you have a, I think there was one I inadvertently recommended doing in the textbook that was a sphere, and it had a density rho that changed with R. You have to integrate over the volume of the sphere to find the charge to be able to do that problem. So you won't have anything like that on the exam. No non-uniform charge densities for volumes, and nothing where you would have, nothing where you would have to do a double or triple integral, okay? I think that means no non-uniform charge densities, but. Okay, so my recommendation is start hitting, I know that we only have a couple of days before the exam, hit it hard. We've got office hours tonight and tomorrow, 4 to 5. And then I might even add another one tomorrow. I'll see what if people need it. Okay, so I'm going to stop the recording. I'll stick around for a few minutes.